So good morning everyone. So up to now we have completed unit 1. So now we are moving to unit 2, that is organic chemistry. In that organic chemistry our first lesson is carboxylic acids and its derivatives. So in that carboxylic acid in derivatives, so first one is preparation of carboxylic acid. Okay, so before going to the preparation, what do you know about carboxylic acid? What are carboxylic acid? So carboxylic acid is an organic compound which has COOH. This is COOH functional group. So such organic compounds are known as carboxylic acid. The organic compound which has a functional group like COOH. So such species are known as carboxylic acid. Okay, let's see how we can prepare the carboxylic acid. So we can prepare the carboxylic acid by number of ways, but in our syllabus we have only 4 methods. So first one is hydrolysis of esters, hydrolysis of amides, hydrolysis of nitriles, and then Grignard reagent. After that we have one more preparation method, that is preparation of aromatic carboxylic acid by oxidation. So as a whole we have 5. Okay, so first one is hydrolysis. Hydrolysis, in that hydrolysis we can prepare the carboxylic acid by hydrolysis of esters, hydrolysis of amides, and hydrolysis of nitriles. Okay, so let's see first one, hydrolysis of ester. So hydrolysis of ester can be achieved uh, by acidic hydrolysis or else basic hydrolysis. So in both ways we can prepare carboxylic acid. Okay, so acidic hydrolysis of ester gives directly carboxylic acid, while the basic hydrolysis of esters gives first carboxylate ion. So this is then further, which is on acidic hydrolysis or acidification, gives carboxylic acid. So by this way we can prepare esters by hydrolysis of ester in presence of acid as well as in presence of base. But hydrolysis of ester, that is in presence of acid, it is considered as a single step. So if you see the mechanism, in that we have the number of steps, but here we direct get carboxylic acid. But whereas in basic hydrolysis of ester, that is also known as saponification, in that we don't get the carboxylic acid. Initially what we get a salt, that is salt of carboxylate, and this salt of carboxylate should be subjected to acidic hydrolysis. After that only we can get our desired carboxylic acid as a product. Okay, so here in this example he has taken ethyl benzoate, then on acidic hydrolysis. So whenever you find H3O plus, that indicate acidic hydrolysis. Hydrolysis means water, acidic means H plus. Whenever proton is added or whenever acid is added to the water or acid is dissolved in water, so the basic character of acid is what? Releasing of proton. That proton initially will taken up by whom? Water. So thereby we get H3O plus. That H3O plus ion is known as hydronium ion. So whenever you see or whenever you find H3O plus or hydronium ion, that means what you are running? You are running acidic hydrolysis, or you can say acidification. So both are same. Okay, so in first case acidic hydrolysis or acidification of ethyl benzoate gives benzoic acid. This is aromatic organic acid along with benzoic sorry, it is not a benzoic acid, so it is benzoic acid, it is ethyl alcohol. Next, look at the basic hydrolysis. In that basic hydrolysis, what happens? Again we have taken aliphatic ester, so that is ethyl benzoate. This is ethyl part and this part is benzoate part. On basic hydrolysis, what happens? So this ethyl ester converted into the salt of carboxylic acid, so that is also known as sodium butanoate. Sodium butanoate. And further acidification, what we get? Our desired one, and that is butanoic acid. Okay, so this is about the hydrolysis. Let's see some more examples. So here see he mentioned as water and sulfuric acid separately, but sometimes he can mention like they may can mention, or some books the authors can mention as H3O plus, or else here water and this is acid. Acid always donates H plus, that released H plus first initially, which will taken up, water will taken up and converted into the hydronium. So this is ester. So on acidic hydrolysis, what we get? We get carboxylic acid along with what? Alcohol. Okay. So let's see the mechanism. So first one is acidic hydrolysis. Let's see the mechanism of acidic hydrolysis. Okay. mechanism. So uh, what is the Fischer esterification? So okay, so let's see the mechanism. So this is the mechanism. So this is carboxylic acid, this is ester, and this is known as a carboxylic group. This is known as C double bond O. That group is known as carboxylic group. And that carboxylic group, what we have? So we have a lone pair of electrons. So these lone pair of electrons are donated to whom? They can be taken up H plus ion from water, that is hydronium ion. It is a reversible step. Okay, so here the driving force is what? Heat of release. Okay, so first whenever so this step is also known as protonation. He mentioned as protonation. Why protonation? H plus ion given by whom? Hydronium ion to whom? This ester. So thereby again we get an oxonium ion. So that is this species, as it is what? Oxonium ion. So this formation of positive charge on oxygen makes this carbon more electron deficient. So whenever positive charge formed on oxygen, that is highly unstable. Why? Because oxygen is a second highest electronegative species. So if you recall the resonance, whatever you have studied in first year, first semester, so in the resonance rules, so you may come across one point, that is what? Residing positive charge on higher electronegative species, that resonating structure is unstable. So here also same thing will happen. So this is undesired. Why? Why? Because higher electronegative atom cannot bear or hold positive charge for long time. So obviously what happens? Instantly what happens? This oxygen will pull up this pi electrons towards it. Thereby what happened? This carbon, that is what? Carboxylic carbon, carbonyl carbon, become more electron deficient, or it become more electrophilic compared to here. So here also we have the carbonyl carbon, but this carbonyl carbon is less electrophilic than this one. Why? Because here what happened? This oxygen got positive charge. So to make this more electrophilic, what we have done? We have done the protonation. So then what happens? This nucleophile. What is here? Water. Water. Why? What is a nucleophile and what is electrophile? Electron deficient species are electron accepting species are known as electrophiles, and nucleophiles are generally electron rich centers, or they can donate electrons. So in organic reaction mechanism, everywhere, every time an nucleophile attacks an electrophile, nucleophile always attacks an electrophile, or vice versa. So that means in this reaction mixture we should have two centers. One is electrophilic center, second one is nucleophilic center. So here see, this carbonyl carbon is an electrophilic center, and this oxygen of water has two lone pair of electrons, so that's why it can act as a nucleophilic center. So this is nucleophile attacks, and this carbonyl carbon facilitates complete displacement of pi electron on oxygen. So thereby what? This positive charge will be diminished. Here see, this positive charge is diminished. At the same time, the oxygen of water molecule acquire the positive charge. Again, having positive charge on oxygen atom, it is called as hydronium ion, that is highly unstable. What happens? Again, to nullify or to diminish that charge, it pulls the electrons from nearby bond. So here this oxygen has nearby bond. Which one? Hydrogen. So it will taken up the proton. So that means this taken up the electrons from of OH bond. So thereby releasing of proton takes place. That proton again taken up by whom? This water molecule. So this step is also be known as proton transfer from this molecule to this molecule. So then what happened? So this proton is removed, and then oxygen relinquish his positive charge, and now this molecule becomes as neutral. So now these two hydrogen, two OH groups or hydroxy group present on same carbon. So that setup is known as geminal diols. Ol means OL, ol means OH group. So here this group is known as geminal diol. This is highly unstable. Why? Because these are two electronegative groups, and when they have electronegative groups, and moreover these are very much near to each other. But because already we have one bulky alkoxide groups, so due to steric hindrance, between these two, what happens? These two molecules readily lose one water molecule. So how? Let's see. So the fourth step is what? Again, transfer of proton from hydronium ion to alkoxide. So again, what happens? Again, formation of positive charge on oxygen atom takes place. That is undesired step. what happens again? This lone pair of electron from oxygen shifts here, so thereby facilitates the cleavage of this bond. So thereby we can get what? Alcohol. So this step takes place. And next step, what happens? Deprotonation. So deprotonation means removal of proton, that is known as deprotonation. So thereby we can get what? Carboxylic acid. So first step, protonation. Second step, nucleophilic addition. Third step, transfer of proton. Fourth step, proton transfer again. Fifth step, elimination of water alcohol molecule. And sixth step, deprotonation. So this is about the mechanism of acidic hydrolysis of ester. So it is one of very important question we can expect in examination. So write the mechanism of acidic hydrolysis of ester. Okay, and next one, basic hydrolysis of ester. So here see, this is complete esterification. This esterification is also known as Fischer esterification. Okay, the reverse of this reaction is known as Fischer esterification. So carboxylic acid reacts with this alcohol, again gives what? Ester. Again we will study this esterification in next lesson. Okay, so the reverse of this step is known as Fischer esterification. Next one is basic hydrolysis. This basic hydrolysis is also known as saponification. So I will show you where we use this saponification, which industry we use this saponification. So saponification is nothing but what? Basic hydrolysis of ester. So see, this one basic hydrolysis is turned to be more beneficial. The carboxylic acid formed during this reaction is deprotonated by alkyl oxide and hydroxide ions, making overall reaction reversible. Okay, so this is about description. So let's see the mechanism. So here see what is basic hydrolysis. So here our attacking species what? Base. So acid means H plus, basic medium is represented as OH minus, and acidic medium is generally represented as H plus, or sometimes it may be represented as H3O plus as protonium. Okay, so this is basic catalyzed or basic hydrolysis, or you can say basic hydrolysis of ester or base catalyzed ester hydrolysis. No problem, both are same. So first step is what? Nucleophilic addition. So this is OH minus, that is a nucleophile, and already in reaction in substrate we have a electrophilic center. What is that electrophilic center? Our carbonyl carbon. So this negative charge OH minus, that is nucleophile, strong nucleophile we can say, that attacks on carbonyl carbon, that facilitates the transfer of these pi electrons completely on oxygen atom. So thereby oxygen will get the negative charge. So residing negative charge on oxygen is a desired one, and it stabilizes. Why? Because it is higher electronegative, so that can bear the negative charge. And next step is what? Again this negative charge shifts here, then facilitates the removal of OH minus alkoxide. So thereby we get what? Carboxylic ion. So actually see, this alkoxide is more basic in nature. So bases, what is base? So according to Bronsted-Lowry, the proton acceptor is base. So this is more basic in nature. It immediately takes up the proton. So this is acid. What is the property of acid? That donates the H plus. So this donated H plus, or this H plus will be taken up by rapidly by alkoxide. So thereby we get what? Carboxylate ion. So this carboxylate ion again participates in resonance. So this resonance is also known as equilibrium equivalent resonance. Equivalent resonance means here see, in two steps, two resonating structure, negative charge is resided on oxygen atom. So this is known as equivalent resonating structures. So this equivalent resonating structures attributes more stability to the carboxylate ion, and also facilitates or also makes this carbonyl carbon as less electrophile than carboxylic acid. So that's why second step, again further this attacking of alkoxide, or you can say base, cannot be takes place. This step do not occurs. Why? Because this carboxylate ion is less electrophilic. Why? Why? Because it participates in equivalent resonance. This is known as equivalent resonance. So due to equivalent resonance, what is equivalent? So in two resonating structure, negative charge is present or resides on oxygen atoms. So in first case on red colored oxygen atom, second case in black colored oxygen atom. So that's why this resonance produces two same structures. So that's why this resonance is known as equivalent resonance. So due to equivalent resonance, this carboxylate ion is more stable than corresponding acid. So compared to this carboxylic acid, this ion is more stable. Why? Because it participates in equivalent resonating resonance. Okay, this step 3, this step is irreversible. It is irreversible. So this is also irreversible. These are reversible. Okay. So this is about the hydrolysis of ester. So we are studying hydrolysis of ester for or under preparation of carboxylic acid. So again, recall the important points. Okay. So this hydrolysis can be of acid can be done in presence of acid or in presence of base. Okay. So this is about the ester hydrolysis. And next one is hydrolysis of amide. So okay. Next one is saponification. What is saponification? Saponification is nothing but base catalyzed ester hydrolysis is known as saponification. So this process generally we use in industry or in industry that to be making of soaps. So this production of soap. So remember, soap is a salt of fatty acid. So this is fatty acid. What are fatty acid? Long chain carboxylic acid. So this is actually, if you replace Na with OH, you will get long chain carboxylic acid. Long chain carboxylic acids are known as fatty acids. And here the salt. Salt means what? What is the property of acid? That releases H plus, and that H plus will be taken up by whom? A base, that is NaOH, and NaOH become water, and we get a salt. That is what oxygen will get, no, sodium ion. So this is known as, so generally what we are using, the soaps are nothing but the salt of fatty acids. So whatever soaps we are using, particularly bath soaps, not for these soaps, butterut ke kadu, bathing soaps, generally fatty acids of carboxylic, salts of fatty acids. So in basic hydrolysis, not base catalyzed hydrolysis, that is known as ester hydrolysis. So this is what glyceryl triester fat. Glyceryl, this is glyceryl. So CH2OH, CHOH, CH2OH. This is glycerol molecule. So that is mentioned in red color. So this is alcohol. This glycerol is attached to 3 fatty acid molecule, so thereby we get the ester. So this ester is known as glyceride ester, triester. So why tri? Because we have 3 ester groups, and these esters are resulted from glycerol. So that's why this fat is known as glyceryl triester. So this is fat. And then basic hydrolysis, what we get? So this is glycerol, and this is what? Salt of carboxylic acid, or salt of fatty acid. So what is fatty acid? Long chain carboxylic acid is known as fatty acid, and salt of this fatty acid, generally we use that one as soap. Okay. Next, another term we may come across in next classes, that is transesterification. So transesterification is nothing but conversion of one ester into another ester. See here, see. So this is ester functional group. Either one side we have phenyl group, and the other side we have ethyl group. And this ethyl group can be replaced with isopropyl group. So this is isopropyl group, 3 carbons we have. So this is isopropyl group. So you can say this is ethyl benzoate. Starting material is ethyl benzoate, and whenever this is treated with isopropanol in presence of acid, we get isopropyl benzoate. So one ester is converted into the higher or another ester. So that process is known as transesterification. Next one is this one, hydrolysis of amides. Hydrolysis of amides. So hydrolysis of amides. So amides hydrolysis can be achieved how? By base catalyzer. So from amides also we can prepare one carboxylic acid. So let's see the mechanism how we can do. So actually amide, so this is carboxylic acid. Okay, so actually one step is missing, I think. Okay, let's see the mechanism. Okay, this is mechanism. Okay, so this is useless part. Let me delete. Okay, so this is also useless part. Okay, so this is the mechanism of amides. So this is amide functional group again. So this is electrophilic carbon. So compared to ester, this is less electrophilic. Why? Because here we are using a strong base, again that is base OH minus, that is nucleophile. So strong nucleophile, this nucleophile attacks on less electrophilic center, that is what, carbonyl carbon. So the first step is addition of nucleophile. It is similar as like in ester, base catalyzed ester. So same phenomena, same thing happens here also. So first step is nucleophilic addition. So attacking of OH minus at carbonyl carbon facilitates the complete transfer of pi electrons or pi bond on oxygen atom. So thereby we, oxygen get the negative charge. So formation of anion. So the second step is elimination of NH group. So again this whereas in ester we eliminated OR minus alkoxide. So this negative charge shifts here, so that facilitates what, the complete cleavage of this bond. So thereby we get nitrogen negative charge. So we may get this group. And again it is again strong basic in nature. Again it accepts the proton from acid. So again see, it is irreversible step. So this step is known as deprotonation. Again deprotonation result what, a salt of carboxylate ion. So again this carboxylate ion participates in equivalent resonance. So thereby it doesn't participates, it doesn't attacked by R minus or RNH minus. Okay, so this is here I given some explanation. And next one, amide, sorry, next one is amide hydrolysis, but here this is what, acid catalyzed amide hydrolysis. So here see, first step as like acid catalyzed hydrolysis of ester. So same phenomena follow here. First step is protonation. So again what, acid. So acid donates the H plus ion. So thereby what we get a oxonium ion. So it is unstable. So immediately what happens, this pi electrons are again are more displaced toward the oxygen atom. So thereby this carbonyl carbon becomes more electron deficient. So at that time here see, nucleophile attacking, here the nucleophile is water molecule. So in the previous case the nucleophile is OH minus. So why we have used OH minus? OH minus is more nucleophilic than water. Okay, OH minus is more nucleophilic than water. So here, but this carbonyl carbon is less electrophilic. But here this carbonyl carbon is more electrophilic. So that's why we are using weak nucleophile. So the attacking of nucleophile facilitates the formation of new OC bond. So this bond, again here what happened, deprotonation takes place. So due to deprotonation we get this one, a neutral molecule. Again further what happens, again the water molecule, here see, we have three nucleophilic centers. This nitrogen has one lone pair of electron, oxygen atoms has two lone pair of electrons. So this H plus ion attacks on nitrogen only. Why? Because compared to oxygen, nitrogen is less electronegative. So less electronegative atom can act as good nucleophile, or it has more tendency of donating of lone pair of electrons. So this nitrogen has more tendency of donating of lone pair electrons compared to oxygen. So that's why this proton attacks on nitrogen. So thereby nitrogen will get the positive charge. Next step what happens, this lone pair of electron shifts here, that facilitate the elimination of NH2 group, amine group. And next again next step is further, next step is deprotonation. So that deprotonation will give what, carboxylic ion, and thereby we get a tertiary ammonium ion. So due to presence of this tertiary ammonium ion, this reaction cannot be reversed. Okay, so this is acidic hydrolysis of ester amides. So these are some more examples. So this is secondary the secondary ester. So or you can say N substituted amide, N substituted or N alkylated amine. So here this is only amide. This is also N alkylated amine. Okay, so I don't think it is required. Okay, next one is hydrolysis of nitrile. So nitriles generally we know as cyanides. Generally we call the nitriles as cyanides. Nitrile is a IUPAC nomenclature. In that IUPAC nomenclature, CN is mentioned as nitriles. Okay, so this is the nitrile. So acidic hydrolysis of nitrile again will give a carboxylic acid. So always it is what we say, thumb rule. So always hydrolysis of esters, hydrolysis of amides, hydrolysis of anhydrides, hydrolysis of cyanides, always we get one, carboxylic acids. Okay, so first step is this one. This is whenever a hydrolysis of cyanides in presence of acid, that gives the carboxylic acid. So here the example, in that first case, it is first step is what? Preparation of cyanide. So here dialkyl halide we have taken, dibromo propane. So whenever this dibromopropane is treated with sodium cyanide, so what happens? Nucleophilic substitution reaction takes place. Thereby we get what? A dicyanide. So penta, penta, pent and dinitrile. So pent and dinitrile, and further hydrolysis it gives our dicarboxylic acid. This dicarboxylic acid is known as glutaric acid. And next, let's see this cyanide. So hydrolysis of cyanide can be done in presence of or achieved as like in previous cases. We have hydrolyzed esters as well as amides in presence of acid as well as in presence of base. Here also we can hydrolyze cyanides in presence of acid as well as in presence of base. So whenever we we hydrolyze these substances in presence of acid, directly we get carboxylic acid. When we hydrolyze these species in presence of base, first initially what we get salt. That salt to be acidic, hydrolyzed or acidified. So then we can get one carboxylic acid. Okay. So conversion of halides. So this is repeated. So that is repeated. Next, amide hydrolysis. So this is also a repeated step. So this is also repeated step. Okay, this is also repeated step. Okay, so again this is repeated. Oh, sorry. This is also repeated. Okay, next one is important one. So this is okay, no need. It is also repeated. Okay. So now see, all these are acid derivatives. So this is first one, acyl halide. And acidic hydrolysis of acyl halide, we get carboxylic acid. This is anhydride. This is another acid derivative again. So acid derivative, hydrolysis of acid derivatives, we get what? Carboxylic acid. So excluding this one, this is not a acid derivative, it is another species. But on hydrolysis of nitrile also we get what? Carboxylic acid. So just this is overall representation of achieving carboxylic acid by hydrolyzing various species. But see here, see, so this one, this one, this one, and this one, these four are considered as acid derivatives. What are those? Acyl halide, anhydride, amides, and esters. So let's see the let's see the reactivity of this one. So out of all these four acid derivatives, out of this acid derivatives, acyl halides, this is acid, this is known as acyl halide, or this is acyl chloride. So hydrolysis of acyl chloride is more reactive compared to remaining derivatives. What are those? Anhydride, esters, and amides. Okay, so the whole thing is that one only. And next one, preparation of carboxylic acids with Grignard reagent. Okay, so preparation of carboxylic acid with Grignard reagent. Okay. So in previous class, in inorganic chemistry, our last topic is what? Organometallic compound. In that organometallic compound, we have seen the synthesis of preparation of Grignard reagent and preparation of carboxylic acid. So when the Grignard reagent is treated with carbon dioxide, we may get the first what? Salt, and followed by acidic hydrolysis, we get the carboxylic acid. And these are some examples. So first step is carbon dioxide. This is Grignard reagent. So first, whenever carbon dioxide is treated with Grignard reagent, what we get? We get a salt. And further on acidic hydrolysis, that salt will be converted into corresponding carboxylic acid. Okay, so this is the descriptive. Okay, next one is oxidation. So this is oxidation. Oxidation. So this is oxidation. So tomorrow we will discuss about the oxidation. Okay, so thank you so much.